now you can actually look into these particular examples. Okay, so we want to see how we determine failures to study whether this particular system will undergo failure or not. So dot bone shaped specimen is examined for static, fatigue, and buckling failures. So we are looking into 3 types of failures. The specimen is made of structural steels. Okay, so if you draw these particular models, okay, then this particular model itself, then we would want with the structural steel. Then the bottom face is specimen is fixed, so you fix the bottom face. Then the top face here, you are applying static pressures of 50 megapascal. Okay, pressures static. So you're under static analysis. So determine whether or not the specimen undergo plastic deformation under the given static pressure. So meaning the static failures will happen or not, will yield or not. Okay. If the static pressure load is changed to into a fully reverse cyclic load of 50, so from if you are plotting the load profile itself, so it's P over time. So at first is like this, 50, okay, megapascal. Static load is like this, right? In the dynamic load, now you change to a complete reverse cyclic load, 50 megapascal. So you have this P megapascal, then you have this now. So here is 50, here is negative 50. Okay, so now if it happen like this, so your load from a 50 static load, static pressures now become a dynamic or fully reverse cyclic loads, 50 megapascal. So we want to determine, okay, because now is a cyclic or dynamic loading already, so we want to determine whether a fatigue failure will happen or not. All right, so of course we have to determine, we have to define how many cycles consider fail. Okay, so usually 10 power of 6, 1 million cycles. Above 1 million cycle is what we call infinite life. So we have to set that. So anything that below 10 power 6 is consider you have consider fatigue failures. So next we would want, because it is standard. Okay, this thing is quite slender. Then it is in compression because we put this 50 megapascal in compression. So it is also good to determine whether it will buckling will happen or not. Okay, so we want to check whether buckling or this specimen will buckle under the given static pressure or not. Right. So we look into that. So you can use I mean the basically the case studies step by step is already including the design modeler as well as the what we call the space claim, okay, in terms of modeling. So you can play around with them, okay, using this. I think it's quite straightforward. So, and in terms of materials, I think also the same. In this case, you do not need to change anything because by default it's structured steel, and this particular model, the dot bone specimen, is a structured steel. So when you have a model, it's so I would want to show you. Okay, so that is something similar like that. All right. So remember to put in your assign your is a structure steel. Then properties wise, if you look into it, the volume is 26x.29, mass is 2.1065. Okay, so please check later on with yours. Then you don't have connections or contacts because it's just one component. It's not like the assembly that I showed you last week. So you don't have contacts. But next we will follow by the mesh. So mesh, I think we can put. We don't really. Our focus today is on failures. So you can put 0.5. Okay. As a mesh size. Okay. So at the end you will see something similar like this. All right. Then very easy. Okay, next will be on the boundary, right? So we put a fixed support at the bottoms. So a fixed support at the bottoms, then pressures here 50. Okay, 50 megapascal on top. So I'm using a fixed supports, okay, at the bottom, and the pressures 50 at the top surface. So I use, instead of using components, right, or vectors, I'm using normal to this surface lah. Right, normal to that surface itself, then it's 50. So you, as long as you make sure that the what we call the arrow is going down on that surface, applied on this surface is good. All right. Of course, after this, we can solve it, right? But we can actually call out the post-process information. We can call for total deformations. That is what we are interested or we are familiar with. And we can also call the equivalent stress, right? So this equivalent stress is the Baumeister stress, okay? Under the DE theories. Okay, we say that it's good for analysis, right? So these two, deformation and stress. Of course, you can use maximum principle. Okay, maximum principle is your sigma ones, or middle sigma 2, sigma 3. Then you have maximum shear stress. Okay, MSS. If you're using MSS, then this stress is using to calculate your static failures, maximum shear. Okay, so here we are using equivalent, because later on we want to use the equivalent so-called DE theory. Okay. So next is calling out the stress tool. Okay. Insert stress tool. Okay. So here is the stress tool that you have. So just now we have talked about maximum equivalent stress. Okay. DE theory. Maximum shear stress, MSS. Next is mole columns. Okay. Solomon theories, okay, and maximum tensile stress, which is your that is for brittle material, MNS, right? So here we are using this structure steel is a ductile material. Then we use the DE theories, or you want to use shear stress also can. So here I'm using equivalent stress, right? So if you click on this, just now insert stress to maximum equivalent stress, then it will pop out of this. So if you expand it, you will see there is safety factors, right? Safety factor coming in here. So this safety factor basically give you the N, right? So if N larger than 1, then it's considered safe. Lesser than 1 is considered not safe, right? But if you have a higher safety factor, if you want to put 2, so then if larger than 2 is good, lesser than 2 is no good. So that is your so-called safety static failures, right? Then we also want to have fatigue failure, right? So you go to insert, right? Under fatigues, so you can call the fatigue tools. So if you click on this, let's say I click one, it's empty, right? It's empty. So first you have to choose, you have to select the fatigue strength factors. Okay, I put 1. Okay, so basically fatigue strength factor is your factors of your stress. So if you are using equivalent stress, right, as your cyclic load, right, so this is 1. So meaning 50, negative 50, 50, negative 50. If you put 2, then this thing is now is 100, negative 100, 100, negative 100, 100, 100. Okay, so that is what it means. So fully reverse is correct. So you can choose whichever. Okay, so we use fully reverse. Then fatigue strength is 1 because I'm using pressure 50, right? The stress that induced also due to this 50, okay, due to this load. Then it's 1, okay, because our question we want a complete reverse stress of 50 megapascal. So the factor is 1. All right. Then the stress, the analysis we have to choose lah. So we are using a stress. We are looking into equivalent stress. So we are determine the stress life lah. Then here the theory. So that is so many lah. So we use Goodman. Okay. The stress components, of course, you can use different type of stress component lah. So here we are using the Baumeister stress, equivalent stress. So the equivalent stress itself, okay, using Goodman theory, okay, and we find this is our equivalent stress. Now our equivalent stress later on, if you solve, you get 216.9, right? Maximum. So here is referring to 216.9 minus 216.9 plus 216.9. So you are using equivalent stress as your stress components, okay? And you are using Goodman theories. All right. Then this setting is done. Then you have to add inserts. Okay. You want to look into safety factor. Okay. So also you want to look into its life. Right. Of course, you can see other things damage index, that's matrix, damage. So we look into safety factors and life. I think is good enough. These two. Okay. Then you can solve it. All right. So once you have solved it, I have solved it already. Okay, so now I'm just evaluating this. So once you have solved it, then you can get the deformations. So the deformations, if you can see this, this bottom, the base is fixed, then you have 50 megapascal, okay, statically loaded. So you will see this is how it moves, how it deforms. Okay, so the maximum is at here is around 0.022 mm, okay, mm. The stress induced, okay, of course, is happening at this curve, okay, the concentrations are at this curve, then is around 216 megapascal. Okay, so this is the equivalent stress, sigma prime, right? Equivalent stress. So if you compare this equivalent stress, if you're using the stress theory is a DE theory, right? Maximum equivalent stress theory. Then this theory, this stress compared with the U strength of this structural steel, then we actually know whether these components or this dot bone specimen will undergo static failure or not. So of course, we can do manually comparison. So, but what we call this analysis will have this stress tool to help you to define the factor of safety. So the distribution of factor of safety. So that is basically telling you, okay, you have a factor of safety, okay, the minimum is 1.15, okay, it's above 1. Okay, so in the case of your factor of safety is 1, that meaning no failures. Right? If your setting of safety is 1.5, then we are saying that this is likely to fail in terms of statics. Right? So here, basically, it tells you the distributions, okay, where is the factor of safety. So at here is around more than 5 So at here, these regions are all at 1.15. So if I say, if I put one above 1 static failure, what I mean, if above 1 safety factor above 1, I assume is safe. Below 1 is failures will happen. Then this thing is safe. Okay, I will say that it is safe. All right, so it's below, well below is U strength, then no U will happen. I will say that, right? So because I have 1.15, it's slightly above my stress induced is slightly below my U strength. All right, then static, we can say that, okay, it's safe because I used 1, okay? My cutoff is 1, okay? Anything above 1, safe, below 1, not safe. All right, then we look into fatigue, okay? So if you are looking into fatigue safety, factor of safety, so you can see that if I have a equivalent stress is 216, right? So if this 216 is previously is static pressure, static stress, now is a completely reverse stress, something like this. 216.9, negative 216.9, positive 216.9, negative 216.9. Okay, if it's like that, okay, I'm using Goodman. Then here, design life is 1 E6. Okay, right? You have to set this 1 E6. Just now I forgot to set here. Okay, so I put 1 E9, so it can be set previously. Okay, so 1 E6, right? So we would actually say that fatigue is likely to happen. It's below, okay, below 1, okay, 0.39. And where the fatigue will happen is basically near these particular regions. Right? Again, the high stress parts. Right? High stress part is at here. So basically, it's near here. So if you want to evaluate its life, right, and evaluate is maybe you want to see the damage. See what is that? Right. So we evaluate it. So because we say that it's below 0.39, right? So this is around 0.39. The minimum is at 0.39, your safety factor. So it's below 1, fatigue is likely to happen. Then definitely you have a finite life of cycles before static will happen. So here, if you're looking into life itself, okay, so at this particular region itself, is the red one, right? Is around 19,000. Okay, 19,000 cycles. Okay, 19,000 cycles. After 19,000 cycles, okay, of this complete reverse stresses, this fatigue will happen. Okay, that's what it means. So if you're looking into damage, okay, same lah. Okay, damage. So at this particular point, okay. So that's why this is not so useful. I mean, looking into life itself is basically anything that above. Okay, here finite life, infinite life. Sorry. Okay, so no issues. But at this particular region, because the stress is large at these particular regions, so you see the distribution is similar. The stress is large at this particular region. So you have a very low factor of safety. You have a low life. Okay, so meaning at here is a finite life, 19,000. All right. So that is what it means. So I would want to share this with you. All right. So then we next one part A, part B is done. Static. So here we are saying that static, yeah, not so likely to happen because it's above 1. Fatigue, the safety factor is 0.39, so it's likely to happen. And life is around 19,000, right? So that is what we can get. Next is buckling, whether it will buckle or not. So if you want to do buckling, then you have to find this eigenvalue buckling. So at here, okay? So you drag this thing up to sharing your whatever data up to solutions, okay? So you can pull it, don't release yet, then up to solutions. You share up to the solution of this static data, then you release it, okay? Then you have something similar like that, okay? So it will share the data, engineering data, the material, the geometry, the models, as well as the solution that you have done previously. Okay, so if you open this, then there is a backlink coming here. Okay, connected. So here you need to do some settings, initial settings. Okay, so the question asks you to find the maximum 3 modes. So you have to set this to 3. Then remember to exclude the negative load multipliers. So you are getting all the positive loads, right? Positive load meaning coming down at its compression, then are all positive related, right? Not the pooling types. So all is compression types, right? So you have to change from program control to no, right? Then yeah, you can start. Right click, then insert deformations, total deformation. So you want to see how it moves, the modes. So here you add 3 because you set here is 3 modes, right? So you have mode 1, the second one, mode 2, the mode 3. So from here, after you have set this, you can solve it, right? Solve it, you can find out that okay, you have these three modes, okay? The load multiplier is 0.78, 2 and 5.7. So what does it mean? Okay, so meaning if you have a 50 megapascal of pressures acting on it, okay, I only need for the first mode to buckle like this, for it to buckle like this, Okay, for it to buckle like this, in this particular mode, in this particular motions, when it compress, okay, you press on it. If you want it to buckle like this, you only need less than 50 megapascal. It's 0.78 times 50. So 0.78 times 50 megapascal. So 39 megapascal, around 39 megapascal, it already can cause it to buckle like this. So that is what it means. So I will say anything that the load multiplier below 1 means it will buckle. Okay, you are putting 50, so meaning it will buckle. Okay, so 50 megapascal itself will cause buckling in this particular mode, in this particular shapes. All right, so it only need 39. So if you want it to buckle like this, okay, if buckle will only happen, okay, something similar like this to happen, okay, buckling some in this particular mode is 2 times of your loads, which is 50 times 2. So 100 megapascal, if you are putting 100 megapascal, then buckling likely to happen in this particular form. Of course, as well as this particular form, right? This one already lower, right? If you're putting 50, then buckling will happen, but in this particular modes. If you're putting hundreds, then combination of these two, okay, the buckling will have it's likely to happen, right? Then the third one, of course, is a higher order buckling. I mean, so now is the first order, second orders, and thirds. Okay, this you need 5.7 times of your load, the current loads, which is 50. Here you are putting 50, so 5.7 times 50, so 5.7 times 50 meaning 285 megapascal. Then probably it will buckle. You have these shapes of buckling. All right, so that is 3 types of analysis in terms of failure analysis that where you can evaluate your designs. Okay, you can use to evaluate your designs. Okay, so buckling, of course, is things to do with anything that slenders under compressions. Then yes, for example, this one, yeah, you can do buckling. All right, so that is about failure analysis, right? So one thing I need to highlight here, because if you are clear with this, okay, from static to fatigues to buckling, so particularly on static and fatigues, so here you see that I will want to highlight a little bit where is our next week's topics, which is where include dynamics. When we are doing dynamic analysis, particularly vibrations, then you will see that fatigue could be even worse. Okay, could come even faster. Right, your life will be even shorter. Right, if you consider the vibration aspect. Okay, vibration aspect. So here you see, maybe I can explain it a bit to you at here. The equivalent stress. Okay, this equivalent stress is 216.9. Right, so it's subjected to a static pressures of 50 megapascal. All right, then we assume under fatigue analysis, we only assume this static, what we call this particular 50 megapascal. Okay, this 50 megapascal now is become a complete reverse loads. Okay, that give you completely reverse stress 216.9. Okay, so here the stress itself here is 216.9, negative 216.9, 216.9, negative 216.9. So it is sinusoidal functions. All right, but in this particular case, it doesn't consider the frequency of this sinusoidal. Okay, so next week we will look into how under dynamic analysis or vibration analysis, we consider the frequency of these particular sinusoidal functions. Okay, will I still have under this 50 megapascal? Okay, if I consider the cyclic, this cyclic so-called load itself is due to this 50 megapascal, but we consider the frequency of this. Okay, will I still have 216? Okay, I mean the stress induced is still 216.9? Okay, so if I consider the frequency functions coming into play, so later on you will find out that this 216.9 is only assumptions, okay, from statics. Okay, so if you are looking purely on statics, right, so it may not be 216.9. Okay, it's not 216.9 negative 216.9 if you consider the effect of frequency. So you will see that it is far larger than this 216.9 at certain frequencies. Okay, then your fatigue, what it means, if this is far higher than 216.9, meaning fatigue, your safety factor will be far lower than 0.39, your life will be far smaller than 19,000. Okay, so if you consider frequency, so up to this stage, okay, our fatigues analysis, okay, we are assuming our what we call this fluctuating load or completely reverse load itself is not a function of frequency, so it's not affected by the frequency of this so-called completely reverse. Okay, so we are assuming the load itself or the stress itself, okay, is purely from the static. Okay, 216.9, then I assume it 216 negative 216 216 negative 216. That's it, right? So that is without considering the dynamic effects. Okay, but just assuming now my equivalent stress is a dynamic. Okay, it's just a completely reverse. That's it. Okay, put 216.9 become 216 negative 216 216 negative 216. That's it. Okay, so next week, if we are coming into dynamic analysis, you will see that how significant is the effect of frequencies. Okay, if you consider the effect of frequency, fatigue, okay, will happen even faster. Right, shorter life. You will have a shorter life. All right, so that is about failure analysis. So next week we'll revisit after we have come into dynamic analysis, particularly vibrations analysis. Then we will come back to here, we revisit this particular problem and see how the effect of the frequency or what we call the vibrations effects, okay, dynamic analysis effect coming into play here, and how we so-called revise our so-called this fatigue analysis results in this case.